Welcome to our help video on the 2-12 lab demonstrations. This is a very important set of demonstrations to come away understanding as the basis behind what actually takes place during a chemical reaction is explored in these demonstrations. So, this is a huge thing to get comfortable with understanding, because when you begin to take a look at what happens as energy changes accompany chemical reactions, you are getting at the heart of what is really happening as a chemical reaction is occurring. In our first demonstration, we'll take a look at what's happening. In this first demonstration, we have solid aluminum reacting with solid iodine in the presence of water to produce aluminum iodide. Solid reacting with a solid. Now, in order to get two solids to react, we sometimes need a vehicle to help them mix together. In this case, that vehicle is water. Water works as a catalyst in this reaction by acting as an intermediary between those two substances, helping them to get in closer contact with one another. So water itself is not involved in this chemical reaction. It's just helping it to occur. That's what catalysts do. So how do we know what kind of reaction was happening here? Well, we saw all kinds of things happening here, but namely we saw a big flame jumping out of the chemical reaction. That is one thing we saw. It was difficult to see if there were color changes because we started with aluminum, we had iodine, and the product was being blocked by the flames and that purple gas that was coming out of the reaction. But there would have been a color change. Because aluminum is a metal, it was a gray powder because they had ground it up. Iodine started off of those little spheres of iodine. It was a solid, and they kind of ground those up. The purpose of having a powder and then grinding up the iodine was the smaller it is, the easier it is for it to react with other substances. So the size matters in this case in terms of smaller surface area allows greater contact for the reaction to occur. But our big evidence was the flame. That flame is definitely energy being produced, and when energy is being produced, it is an exothermic reaction. So we saw the flame. Number two, we know it was exothermic. What was this purple cloud coming out of the reaction? The purple cloud was very interesting because we have a solid reacting with a solid in the reaction, producing a solid. So the gas that we saw was not any of the reactants, or was not a product. I'm sorry, the gas that was produced was not a product. We see no gas on the product side. So what was that gas coming off? What was the purple cloud? Well, we know that this reaction was generating heat. Iodine starts out as a solid. When the reaction occurred, if you remember, the demonstrator kept mentioning that the iodine was present in excess. That means that the experimenter purposely put in abundance, more iodine than was needed. So when the aluminum began reacting with the iodine, there was iodine left over. So there was solid iodine left over being exposed to the highly exothermic reaction. So what did all that heat energy do that was being given off? It turned the solid iodine into a gas. That was the purple cloud you saw. Gaseous iodine. The next thing they're asking us to do, and this is very, very important for what we're going to be learning in this particular demonstration, but they wanted us to draw a sketch of the energy diagram. An energy diagram looks at what is happening to the energy in the course of a reaction. I've highlighted the draw a sketch in purple because the sketch right here, there's so much things written here. You're like, where's your sketch? Where's your sketch? The sketch is the purple line. So the energy starts out here. Here's my reactants. The reactants were the solid aluminum and the iodine. And we have the 2 after the iodine, I should mention, because that's part of Brinkelhoff. I's come in 2s. It's a diatomic element. So you can't get one atom of iodine alone. They join up in 2s. So we have iodines joined up in 2s. So for the reaction to occur, we need to break those iodines up. So the energy starts right here. This is our initial energy right here on this line. This blue line is the energy of our reactants as the reaction begins, or this is the beginning amount of energy we have. In order to get the reaction to occur, we have to break the iodines, which are chemically bonded. One iodine atom is covalently bonded to another atom to make the I2. We have to break those bonds. So we have an iodine bonded to another iodine. They're bonded together. We need energy to break them apart. So energy must be added in to break the reactants apart. So right here, the graph starts going up because that is the energy needed to break the iodines apart. Once the iodine atoms are broken apart, then they can begin reacting. So the line, here's the energy we started at. This red line going up is the energy we added to break the iodines up, to get everything ready to react, to activate the atoms so that they're ready to react. That red line is the energy we put in to break apart the reactants. That's the definition of activation energy. The energy needed to break up the reactants, to break the bonds holding the iodines together. Energy always has to go into a reaction in order to get the reaction going. That's called the activation energy. So there is an endothermic step to the reaction. We're not saying the reaction is endothermic, but there's an endothermic step to the reaction. Energy goes in, that's the activation energy. Now right here at the top of this hill, at the top of this purple hill, where this black dot is, this is where the reaction or the formation of the products begin. So going up the hill, we're getting everything ready to react. We're activating things so that the reaction can form, so that we can begin forming the product. Right here at the black dot, as it says down here, the dot at the top of the hill, the product starts to form. So now we're forming the product and energy is being given off. When the product forms, energy is being released. Energy now starts coming out of the reaction. Why is energy coming out of the reaction? Because we're forming new bonds. The iodines are now joining up with the aluminums. We're forming product. So right down here where the graph levels up, we now have formed the product. The product is all formed. The aluminum iodide is formed. And the process of forming it involved the new bonds forming, which released energy. So to break bonds, it takes energy. As new bonds form, energy is released. So now energy comes out. So all reactions involve some energy going in to break the bonds and some energy coming out as new bonds form. Whether the reaction is endothermic or exothermic, overall, enthalpy is the word used to what is the overall energy change. Some went in, it looks like more came out. Some went in to break it apart, more came out. How do I know that? Because this line, the outline, is bigger than the inline. The enthalpy involved a lowering. The energy was overall, more came out than went in. When more came out than went in, energy was given off to the surroundings. That is a minus sign. Energy was lowered. It was given off. The overall change in energy, which we call enthalpy. Enthalpy involves comparing what went in to what went out. If what went out was bigger than what went in, then energy was released. If energy was released to the surroundings, it's minus. How much energy was released? Well, here's the energy we started at. The blue line was the energy we started at. The energy we started at is a higher level than the energy we ended at. This is the energy final, E2, this orangish line. This is where the energy ended. It is lower than what we started at. So the energy was lowered. We went from this line down to that line. That line is lowered. It's a minus delta H. So how do we know if it's exo? One way is the reactants are above the products. Here's my reactants right here. Here's my products right here. The reactants are above the products. So energy dropped. It was lowered to get to the products. That meant energy had to be released. Why was energy released? If it's exothermic, what do we know? Well, we know that overall a lowering of enthalpy is desired in the universe. The universe is tending towards lower enthalpy. Why is it tending towards releasing energy? Well, you could say because the stability goes up. Anytime there's a trade-off, if the energy goes down, the stability goes up. Again, if energy goes down, stability must go up. That is the trade-off in the universe. So by lowering the energy, the reactants had higher energy, the products had lower energy. By lowering the energy, we improve stability. We can say that Ali3, aluminum iodide, must be more stable than the aluminum and the iodine alone. Also, that is the important thing to recognize, the trade-off between energy and stability. Down here it says if the down arrow is bigger than the up arrow, it's exothermic. If the down arrow, the energy out, is bigger than the up arrow, the energy in, we know it's exothermic. There was a lowering of energy, and here is the net change right here. This is the net change. The blue line down to the orange line. That line is found by taking this energy in. The energy outline is bigger. The energy outline is bigger. If you take the energy in line and subtract the energy out line, the difference between the two is this, and it is a drop. Energy in minus energy out. The out is bigger, so it's negative. We know it's exothermic. In our next video, we'll talk about the next demonstration. Hopefully this clears it up a little bit. This is an important graph to understand. If you have questions on this energy diagram of an exothermic reaction, don't hesitate to ask. Thanks for watching.